begin with our first session. To moderate this session, I would like to invite my colleague, Dr. Muhammad Danish, who is Assistant Professor in Civil Engineering section, to kindly moderate this session and to take over from now.
Good morning, everyone. Now, this is the first session of day 5. The title of this session is Modeling and Analysis of Functionally Graded Structures. This lecture will be delivered by Mr. Ateeb Ahmad Khan. Ateeb Ahmad Khan completed his Bachelor of Technology degree from Aligarh Muslim University at the Department of Mechanical Engineering. In 2013, he graduated with a first-class honors degree in Mechanical Engineering. He was then granted a scholarship by UGC for qualifying GATE and completed his Master of Technology degree from Aligarh Muslim University at the Machine Design section of Mechanical Engineering Department. In 2015, Ateeb Ahmad Khan graduated with a first-class honors degree in Mechanical Engineering and was awarded 2 gold medals for securing his first position in the university. In 2015, he went to Berlin for his doctoral degree at the Technical University of Berlin, under the guidance of Professor Christina Völlmecke on the topic Analytical Modeling of the Mechanical and Buckling Behavior of Functionally Graded Sandwich Structures. Presently, he is working as Assistant Professor in the Department of Mechanical Engineering. And now I would like to invite Mr. Ateeb Ahmad Khan to proceed the lecture. Mr. Ateeb Ahmad.
Yeah. Good morning, Dr. Danish, and thanks a lot for such a nice introduction. I would also like to thank Dr. Imran Shafiq and his team for giving me this opportunity to present my ideas on functionally graded material and my research in front of such a learned audience. Good morning, dear participants. As Dr. Danish already told you, I am Ateeb Ahmad Khan, and I'm working as Assistant Professor in the Department of Mechanical Engineering at Aligarh Muslim University since 2016. And my research area includes the modeling and analysis of composite structures, sandwich, and functionally graded structure, both type of modeling, analytical and finite element modeling, and also impact mechanics. However, today's lecture is on modeling and analysis of functionally graded structures. So before barging into the modeling and basically the mechanics of functionally graded structures and the modeling techniques of FG structures, let's try to answer a few of the queries which came to my mind when I first heard this word FGM. Now, the question which made me curious was why the need of FGM was felt, and what were the conditions under which the composite material, which is also a very great material, and it has been used widely in different applications. So what was the reason, or what was the condition under which that composite materials failed? And lastly, what are the areas of application of the functionally graded material? So these are the queries basically which I want to address first. So in my first module, I'll be addressing why, what, and where of FGM, followed by some of the manufacturing techniques of the functionally graded material. And then in my second module, I'll be basically explaining you the difference between different equivalent single layer theories, and then how to use it for the functionally graded material. And specifically, I'll be considering classical laminated plate theory, the third order theory, and a higher order theory given by Dr. Kim and Chow. Later on in this lecture, I'll be basically discussing the modeling techniques of the functionally graded structures. And towards the end of this lecture, I'll be showing you some of the results which I've obtained, the deflection of the plates and the stresses which are developed in the plate, and the buckling loads which we need to calculate for the functionally graded material. I'll be showing you that for the simply supported plate. Now, these results are obtained from in-house developed code by me, and it is only for the simply supported, as you know that the analytical solution is basically possible only for simply supported cases. And I'll be showing you some of the results obtained from Abacus, and I'll be discussing you how to model this type of material in Abacus. And the results which are extracted from Abacus are for the cantilever beam, for the basically all sides simply supported beams, all side cantilever beam, and two sides cantilever and two sides free plate. Now this is just for you to see the comparison between the simply supported conditions and the clamp conditions, and just to verify that the results which I obtained from the Abacus are also in good agreement with the literature already present and with the in-house developed code. So starting with the lecture, let's see what are the conditions under which the other materials fail. So starting with the very basic material, which is a pure metal. Now pure metal is of very little interest to the design engineers. But the reason being it is of little interest because of the conflicting properties. Now this word is important, and in order to elaborate on this conflicting properties, I'll be taking two examples of aluminium and iron. Now, aluminium, as you know, is a very lightweight metal. Okay, it is a very lightweight metal, but then the strength of aluminium is also low. So wherever the application asks for a low weight and high strength material, we cannot use aluminium. On the other hand, iron has a great strength, but then the weight of iron is also very high. Now, just to make you understand better, I'll basically tell you the density of aluminium is around 2.7 gram per centimeter cube, or 2700 kg per meter cube, and that of iron is around 8000 kgs per meter cube. So you can see the difference in density is very high, 2700 for aluminium and 8000 for iron. But on the other hand, the strength of aluminium is only around 90 megapascal, and for that of iron is almost 600, or near about 550 megapascal. So again, the difference in the strength is very high. So this is the reason because of which the pure metals are of little interest to the design engineers. Now, this problem of conflicting properties can be solved with the alloying. Now, bronze, which is an alloy of copper and tin, was the first alloy that appears in the human history. And the reason for basically alloying the tin with the copper, or mixing tin with copper, is that tin increases the machinability and it increases the hardness of the copper. So when they are combined, both of them are combined, they form bronze, and which is again a useful metal in human history. As you all know, we have a dedicated Bronze Age in the human history. And the reason for using copper is to increase the ductility of the material. But having said that, there are some issues associated with the alloying. And the first limitation is that there is a limit to which one material that can be dissolved into another material because of thermodynamic equilibrium limit. Okay, so unminded that this mixing is on the atomic level. This mixing is basically on the micro level. And the other limitation associated with the alloying is, suppose you have two metal or two materials, material A and material B, and their melting points are very wide apart. Okay, the melting points, when the melting points are very wide apart, it is almost impossible to make an alloy of these two materials. Now again, this problem of wide apart melting point can be solved by using a technique known as powder metallurgy. What happens in powder metallurgy is that we take powders of both the materials and then we mix it together. We weigh it and then we mix it together, and then we go for ramming and then for sintering of the material. But then the problem again with the powder metallurgy is that the structures obtained from powder metallurgy techniques are very porous, and they have very less strength, or they are weak. Now here comes in our composite material, which gives an excellent combination of the properties which might be different from the individual parent material. And the best part with the composite material are that they are very light in weight. So let's see what are composite material. Composite, as the name basically means, consisting of two or more distinct material. Now, composite material are the materials made from two or more constituent materials with significantly different physical and chemical properties that, when combined on macro level, produce a composite material. Now, these two words are important, that with significantly different physical and chemical properties mixed on macro level. Now, as we were discussing in alloys, that when the melting points of the two materials which are to be mixed together are basically wide apart, we cannot make an alloy of that thing. But we can make a composite material with those two materials. Okay, because the parent material might be significantly different in chemical and the physical properties. And the next point is that they are mixed at macro level. Okay, whereas in alloy we were mixing it at micro level. Now, in order to give you basically the effectiveness, in order to tell you the effectiveness of the composite material, I would like to consider an example of concrete. Now, concrete, as you all know, has a very good or great compressive strength, but the tensile strength of concrete is very bad. In fact, the tensile strength of concrete is only 10% of its compressive strength, which is very low. But then this problem or this tensile strength can be increased by using a composite material which is known as reinforced concrete, which is basically is a type of fibrous composite material where the steel rods are inserted in between the concrete. Now, a steel rod has a very good tensile strength, and it is from the steel rods that the tensile strength of the reinforced concrete is increasing. Again, just to give you a small comparison, the tensile strength of a concrete is only 2 to 5 megapascal, whereas that of reinforced concrete is almost near 100 megapascal. So you can see that just by inserting the basically the steel rods, the tensile strength of the concrete or the reinforced concrete is significantly increasing. Now, there are different types of composite materials. The first one is your fibrous composite material. The second one is your particulate composite material. And the third one is your laminated composite material. Now, in this figure, you can see that there is an example of laminated composite material where different lamina, this one is first lamina, this one is second one, the third and the fourth and the fifth one. These are the different laminas which are binded together to give you a laminated composite material. And you can see that the fiber angles over here is 0 and the fiber angle over here is 90. Now, again, the fiber angle basically affect the strength of the fibrous composite material to a great extent. So these are basically this figure will show you the different types of composite material, and the first one is your fibrous reinforced composite material. Now, there are two types of fibrous reinforced composite material. The first one is continuous fiber reinforced composite material, and the second one is your discontinuous fibrous composite material. Now, as the name suggests, this continuous fiber reinforced material are the materials where the fibers are continuous throughout the length of the composite material. And in case of discontinuous, it is basically it does not run throughout the length, and it is randomly placed, or maybe it is aligned to some principal material direction. Now, an example of the composite or of the continuous composite material is GFRP and CFRP. Now, GFRP is your glass fiber reinforced polymer, which is used at the fuselage of airplanes. And CFRP is your carbon fiber reinforced polymer, which is used in the racing cars and for wherever in the automobile, wherever high strength is needed. Now, as you all know, that glass as a bulk does not have great strength. Whereas when the glass is drawn into the fibers, it has basically the strength increases significantly. And the discontinuous fiber reinforced material is, the example of discontinuous material is a straw in mud bricks. Now, straw has been used in mud bricks since a long time, and it is to strengthen the mud bricks. And mud acts as a matrix material. And then again, the properties of the matrix material is to support the fibers and to transfer the load among the fibers if they are broken, and to give the final shape and finish to the material. Now, coming to the second type of composite material, which is particulate composite material. There are four types of particulate composite material, and particulate composite material is again where we use small particles of one material into the matrix of other material. There are four combination of particulate composite material: metal in metal matrix, metal in non-metal matrix, non-metal in metal matrix, and then non-metal in non-metal matrix. Now, the example of these are the first one is lead in copper, or you can also consider tin in copper. The purpose of mixing lead or tin in copper is same, just to increase the machinability and to give hardness to the copper. The example of other type of particulate composite material is aluminum paint. Now, what happens in aluminum paint? Basically, the aluminum flakes are suspended into the paint, and the purpose of that, it gives a better coverage on the painted surface. Another example of such type of composite material is solid propellants, which are used in rocket. Now, the example of non-metal in metal matrix is cement. Cement is basically your ceramic material in the metal matrix. It could be oxide based or carbide based, and then it is used basically in the control rods in a nuclear reactor. And the last example and the best example which I can give you of such type of composite material is concrete. And the last type of composite material is your structural composites, which is sandwich composite. So sandwich composites are.
Dr. Ateeb,
Yes,
there
sir.
is a question from Dr. Balachandran.
Yes, sir.
I don't think I think he wants to clarify something. He's asking
Yes,
that concrete is itself a composite, and
yes, sir.
RCC is another composite type.
Yes, sir. Yes, sir. He's absolutely right. Concrete is already a composite.
Yeah. So, Dr. Balachandran, if you want to ask something else,
Actually,
you can.
okay. Dr. Balachandran, actually, you are absolutely right. Concrete is a type of composite material, but I have basically compared concrete and reinforced concrete because this is a very common example and everybody is aware about concrete and reinforced concrete. And just by using the fibrous type of composite, you can see that the strength is significantly increasing. As I told you, that the tensile strength of concrete is somewhat near about 2 to 5 megapascal, whereas for fibrous composite, sorry, for the fibrous reinforced concrete, the strength is near about 100 megapascal. So you can see that almost 50 to 60 times the strength is increasing. Shall I move ahead, Dr.
Yeah,
Balachandran?
please.
Okay, okay. Yeah, so I was telling you about the sandwich composite. It is same as laminated composite material. Different lamina of the materials are used at different angle, but at the center we use a different core. It could be any material, it could be any metal, it could be aluminum, it could be iron, or it could be any material, and it could be even honeycomb structure. So basically, the idea is to sandwich a different type of material in between the laminated composites. So this was some type of composite material. And yeah, when I was talking about GFRP and CFRP, it was a good time to tell you that the effectiveness of the composite material is basically judged by the ratio of its strength or stiffness to its density. So either we use strength to density ratio, which is a specific strength, or stiffness to density ratio. Now, this table over here will tell you why I was emphasizing that composite materials are better or alloys are better than metal. Now you can see that the specific strength of copper is only 25. And as we move down to alloys, it is 158, 204. So if you compare the specific strength of copper and aluminum alloy, it's almost 10 times. Okay. And again, if you compare this aluminum alloy with the Kevlar, which is a composite material, from here we have a composite material from carbon epoxy composite. These all are composite material. Now, the specific strength of composite is very high when compared to alloys. It is almost 10 times. Okay, so this table is just to show you that how the specific strength is increasing as we are moving from metal to alloys and from alloys to composites. Now, having said all the advantages of the composite material, in the starting I told you we will be discussing why the composite material failed or under what condition it failed. So basically composite material fail where under extreme temperature condition. And it basically fails. Suppose we are having two lamina. This is of lamina of material A and this is lamina of material B. Now these two lamina, both of these are having different coefficient of expansion. So at room temperature, they will perform, they will perform normally, but at elevated temperature, what will happen? This has different coefficient of expansion, so it will expand at different rate. Similarly, this has different coefficient of expansion, and these coefficient of expansion are very wide apart. So they will expand at different rates. So what will happen? Delamination will occur. So this layer will no longer be sticking with this layer, and this layer will separate out. And obviously, the strength which we have calculated for that particular laminated composite material is when both the layers are acting together or both the layers are carrying the load together. Once they are separated, the strength of the complete structure will drastically come down. Now, there are two types of problem with this composite material. The first one is debonding. Now, this occurs when the adhesive stops sticking. Whereas, basically, if the adhesive between these two layers stops sticking, then there will be the case of debonding. And as I already told you, if the coefficient of expansion for these two materials are different, so they will expand at different rates at elevated temperature, and there will be a problem of delamination. Now, researchers in the mid 1980s came across a problem where they have to design a hypersonic plane. And this hypersonic plane has to bear an outside temperature of 2000 Kelvin and an inside temperature of 1000 Kelvin in less than 10 mm of thickness. And the solution to this problem is what we today known as functionally graded material. So functionally graded materials are being used starting from the 1980s, but very recently after 2000, it basically gained some popularity. Anyhow, this is how your functionally graded material was invented. Now, let's see what is a functionally graded material. So functionally graded material is a material which is characterized by the variation in the composition and structure gradually over volume, obviously resulting in the corresponding changes in the properties of the material. So as I have considered the previous example of laminated composite material, where I am using this as one layer and this as another layer. So you can see that at the interface, basically the composition of the material from this to this is basically changing abruptly. Whereas what happens in the functionally graded material is that, suppose this is the height of some material. And what we are saying in functionally graded material is that the composition will gradually change from bottom to top according to a function, which is already predefined function. And the elastic properties will correspondingly change from bottom to top. So here you can see that I'll show you a figure, which after that it will be more clear to you. Just a second. Yeah. Over here, you can see that this is an example of a composite laminate, and this is an example of FGM. Here you can see that from at this point, the composition is changing abruptly from this pink laminate to green laminate, and similarly from green laminate to this red laminate. So at the interface, this composition is changing, and that's why there is a problem of delamination, or it might be a problem of debonding. Whereas in case of FGM, if you move across this direction, at the bottom we have 100% ceramic rich material, and at the top we have metal rich material. And as you can see that there is no distinct point after which you can say that, yes, this material is changing from material A to material B, or the material is changing from ceramic to metal. So as I told you that the change in composition is gradual across this direction, and hence basically the engineering constant will change gradually across this direction. So this is the major difference between composite and FGM, and this is why the problem of delamination and debonding is very rare in case of FGM. And generally we use FGM basically one of the material used in FGM is a ceramic, and other material which we uses in functionally graded material is a metal. Okay. So some of the features of the functionally graded material are listed in this table. It can withstand high temperature gradient over small thickness. So as you all know, this is the reason in the first place functionally graded material was invented, so that it can bear high temperature gradient over a small thickness. Second one is gradual transition of microstructure. As I explained you in the previous slide, that the transition from one material to other material is gradual, and there is no distinct point or distinct line after which you can say that the material is changing from material A to material B. The third one is it minimizes the stress concentration because of obvious reasons. And the fourth one is your tailored functional performance. Now, as I told you that the change in composition is governed by a function, and if you change that function, the change in composition will also change, and that's how you can tailor the performance of your functionally graded material. You can change basically the volume fractions of one material to change the performance of the structure. So these are few of the features which are listed in this table for functionally graded material. So this was why and what of functionally graded material, why we use functionally graded material, and what are functionally graded material. Now let's see how basically or what are the areas of applications of functionally graded material. But before that, I just want to tell you that there are two types of composite material. Actually, the original type of composite material, as per the definition, is continuous structure. But sometimes what we do, I also have a paper on this on stepwise structure, wherein I have basically made a FE model, finite element model of a beam, and then tested this stepwise structure. So from the manufacturing point of view, it is easy to manufacture a stepwise FGM. But although as per the definition, the correct type of FGM is this one, where the change is gradual. But what happens in stepwise, the change is although the change is not that gradual, but yes, somebody wants to ask any question?
There is a question from Dr. N. Meenakshi Sundaram.
Yes,
so please go ahead, Dr. N. Meenakshi Sundaram, if you want to ask something.
No, say, sir. Questions regarding the. Sir, good morning, sir.
Good morning.
Is it correct to say functionally graded material is a type of particulate laminate? From your presentation, is it correct observation or inference, or it is a difference?
Sorry, Meenakshi, can you please repeat your question?
Sir, is it audible, sir?
Yes.
I'm audible, sir. Yes, sir.
Yes, you are audible.
Sir, it's a simple question, sir. From your presentation, I came to understand, that is the infer, that is the functionally graded material is a type of particulate laminate, or sorry, particulate composite.
No. I got your question, Meenakshi.
Yes,
actually,
that's
you
why
cannot say. You cannot say that it is a particulate composite material, because particulate composite materials are homogeneous. Everywhere the composition, if you take a small part of a particulate composite material, the composition will be same at every point. But in case of this FGM, the composition is gradually changing. So obviously, if you take a plane, if you take this plane, suppose you cut. So if you take this plane, so the composition at this plane, if this direction is X and this direction is Y, so the composition across the XZ plane will be same. But as you move in this direction, the composition will keep on changing. Maybe because of this figure, you get confused that this is a particular type of composite. But no, it is not a particulate composite is totally different from FG.
Okay, thank you, sir. Thank you, sir.
You're welcome.
Sir, regarding the concrete also, I want to add some more, sir, some supplement answer. You don't mistake me. So even though it is a concrete is the mixture of 3 or 4 different material, at the
Yeah.
time of mixing, after it become hardened, then it is considered as a single solid like homogeneous material. Based on
Yeah,
this
yeah.
concept only, the design of RCC or plain concrete designs are evolved. So it cannot
Yes.
be a heterogeneous, or it cannot call it as a composite material. Then it is then the RCC is called as the composite material, since it is the combination or the consisting 2 different material. One is the what is that compressive material, another one is a tensile material, equally
Okay,
tensile
okay,
and
okay.
compressive
If
material.
going
So
by your argument, if you are saying
yes,
that it becomes solid or whatever it is,
yes, sir.
so you cannot call it
It's my
composite.
humble because yes, so yes, sir. Please, it's purely you cannot call it as the what is that single material or homogeneous material, but it is the composite. But for the design purpose, we are assuming that the design concept evolved considered
Maybe,
as a single homogeneous material.
maybe the civil engineers consider it
Yes,
as
I'm
a
background of my civil engineer. That's
yeah,
why
maybe
I'm
for the
telling this.
design purpose
Oh,
you make this assumption, but
yes, sir.
concrete is very much composite because composite is anything made up of two materials which is
Two,
not
two
mixed at
different ways,
micro
sir.
level.
Yes, I'm really, I'm
Okay.
accepting your argument, sir. But
Okay.
still then, as a civil engineering point of view, it is a single solid homogeneous. When you are arriving the stress and concept, the assumptions in the design concept, the only thing is concrete is a homogeneous material. They
Yeah,
are
so
assuming that
so
is,
so
it is
we
obeying the
can
Hooke's law, then it is
Mhm.
stress is directional proportions. All things are
Okay,
around, that is arrived based on this concept, sir. That's why I'm adding. Yeah, I'm not arguing,
okay.
sir. I'm just adding
No,
what I
no, no,
know,
no,
sir.
no problem.
Thank
It's
you. Thanks, sir.
always good to have a discussion. It's
Okay,
nice that you
thank you,
people
sir.
are
Go ahead, sir.
saying it in.
Sorry for the
No, no,
interruption, sir.
no, no
Please go
problem,
ahead.
no problem,
Thank you, sir.
no problem. So as Dr. Meenakshi told you that it is basically a homogeneous material, but then composite can also be homogeneous. I said that composite needs to be heterogeneous. Okay, it might be heterogeneous or it might be homogeneous, but whatever he's saying is absolutely correct. The civil engineer, from the design point of view, take it as a homogeneous material. And I was basically of the point of view that composites are those when two or more materials are mixed at the macro level, okay, which can be identified differently. Anyways, moving on with this lecture, I have basically, I believe I've already explained you what is the difference between stepwise structure and continuous structures. Now, moving on to the area of application of FGM. So in the very first application of FGM, you have already seen that it has been used in the aerospace application where you need to make a thermal barrier in a very small, which need to basically withstand a thermal barrier in a small thickness. So that's why, for that reason, it has been used in aerospace application. The second and the most important application of FGM is in medicine. Now, here I would like to tell you that our living tissues like bones and teeth are also the naturally occurring functionally graded material. Our bone is a naturally occurring functionally graded material. Our teeth is again a naturally occurring functionally graded material. So basically, in order to replace these tissues, a compatible material is needed, which will serve the purpose of the original biotissue. So that's why in the medicine field, this FGM materials are used. And FGM implants are basically a lot of research is going on FGM implants. And there is basically what I can think of is there are three main reasons of using FGM implants in place of metal implants are the first one is it improved the biocompatibility with bone tissue. As I told you that our bones and teeth are already naturally occurring FGM, so we need a compatible material to replace them. The second point is basically it prevents the thermal mechanical failure, or at least it reduces the thermal mechanical failure, because it can, as I already told you, that it can withstand a great thermal gradient. Now, the most important reason why FGM are used in the medicine field or in this FGM implant area is because of the reduction is in stress shielding effect on surrounding bone that usually arises in the presence of metallic joint. Now, this stress shielding effect might be new. This word might be new to you. So I'll explain a little bit about this. This is basically a effect in the which cause in the reduction in the density of the bone as a result of the removal of the typical stress from the bone by an implant. So what happens is that when you remove a bone and you insert a metal implant, so initially there was some stress which was coming from that bone which you have removed, and which will not be same as your metal implant. So and usually it is lower than the pre-existing bone. So what happens is that there is a law which is given by Wolf, and we call this as Wolf law. And our bones are very smart structures. They are very, very smart structures. And it basically bone remodels itself in response to the load it is placed under. So when we basically remove a bone and we bring in this FGM or sorry, a metallic implant, so what happens is that the stresses which are caused by that bone previously is reduces, and hence the density of the bone reduces because the load on that bone decreases, and this is happening because of the Wolff's law. Now, this is what we call as a stress shielding effect, and this stress shielding effect is again significantly, basically it reduces significantly in case of FGM implant. So that is the reason why FGM are used in the medicine field. Now it is used in defense because of its crack basically because of its property to inhibit cracks. It is used in armor plates and bulletproof vests. And then it is also used in energy sector. This point will be more clear to you when we will talk about the manufacturing of the FG materials, where we will talk about a thin FGM material and the bulk FGM material. What happens is that sometimes we coat a pre-existing material with the FGM material. Only a thin layer of that material is used. So what we can do, we can coat the turbine blades with FG materials, so it provides a thermal barrier, and it acts as a protective coating for the turbine blades in gas turbine engines. Some of the other applications of the FGM are cutting tool, insert coating, automobile engine components, and etc. So this brings me to the end of the first module, and where I wanted to discuss the why, what, and where of the FGM. Now coming to the manufacturing part, as I told you that there are two types of FGM from the manufacturing point of view. The first one is thin FGM and the second one is bulk FGM. So bulk FGM is basically your complete FGM, the structures which I have already shown, where the basically where the composition is changing gradually over some dimension or over the volume. And then thin FGM is basically a relatively thin section. Already the composition is changing in that also, but it is a relatively thin section, and it is used as a surface coating over some existing material. Now, the fabrication techniques, there are different fabrication techniques for your FGM, and they are listed in this table. The first one is vapor deposition technique. With the help of vapor deposition technique, we can only produce thin FGM. And in case we want to make a bulk FGM with the help of this technique, it will be very energy intensive, and it will be a very long time taking process. So we only manufacture thin FGM from vapor deposition technique. The second one is powder metallurgy technique. There are some advantages and disadvantages associated with this technique, which I'll be discussing. The third one is centrifugal method, and the last one is solid free form fabrication method. Now this SFF or solid free form fabrication method is the best method to basically produce bulk FGM at large volumes. Okay, so let's see briefly what are these different manufacturing techniques. So vapor deposition techniques, as I already told you, is excellent for basically for coating some material. There are two types of vapor deposition technique. The first one is chemical, and the second one is physical vapor deposition technique. Now here I want to discuss about the physical vapor deposition technique. This is basically a setup for the same. At the center, this is a quartz tube, which is kept inside a furnace. Okay, the furnace, the central part of the quartz tube is kept inside the furnace, and both the ends are outside the furnace, and they are basically a cooling water is passed at the ends of the quartz tube at the starting as well as at the ending of the quartz tube. So the idea is basically to heat this central part of the quartz tube, and the reason for that is we want to vaporize this source material. Okay, we want to vaporize this source material. Now, what happens is that this quartz tube is kept inside a furnace, and the source material is kept at the center, and the temperature is raised. So this material basically vaporizes, and we pass a carrying gas, which is generally a noble gas, which does not react with this source material. And this carrying gas basically carries this vaporized material, and it moves forward, and it basically deposits that FG vaporized material on this surface. And this is the reason why we are lowering the temperature at the end, so that this vaporized FG material condenses and gets deposited over this purple material. Okay, so this is how basically this is how the working of physical vapor deposition technique, wherein the material is vaporized and it is carried by a carrying gas, which is generally a noble gas, and then at the end of the quartz tube it is cooled down so that it gets deposited at some material. So that's how we make a thin layer of FGM over another material. Now there are 2 points to consider here. The first one is, somebody's asking some question. Okay, the question disappeared. Okay, so there are 2 problems with this method, and we cannot produce a bulk FGM with the help of this material. It is very slow and energy intensive. And the second one, it is very uneconomical method. So it is only used.
Sorry to disturb.
Yes, sir.
Dr.
Yes,
Ateeb Khan, there is a question from Rituraj.
Yes, sir.
The question is, sir, I will be working on formability of composites. Can you recommend any aluminum or magnesium based composites on which I can work on as far as industrial applications are concerned?
Okay, so I'll be showing you some results on aluminum. You can see later in this lecture that how aluminum and I'll be using 2 ceramics and 1 aluminum, and you will see that how I'll be basically they are performing. And towards the end of the lecture, we can discuss more on this, that what to use, and basically I need to know what is your application and why you are using it. So I request you that if you can reserve these types of questions towards the end of the lecture, so we can discuss there, because most of the points will be covered in this. I have covered, I basically tried to cover all the aspects of FGM. That's why I started with why and what and where, and then the manufacturing, and then basically the modeling technique. So we can discuss this at the later stage when you have a better understanding of FGM and how they are performing under different loads. I hope, Dr. Rituraj, this is okay with you.
Okay, please carry on, Dr. Ateeb.
Okay. Okay, so these were the disadvantages associated with the basically physical vapor deposition technique. Now, the next type of manufacturing technique is powder metallurgy. I believe I have already explained you how this technique works. Basically, we wait and mix the powder, and then we ram it, and then we finally go for sintering. So this is the technique which is used to make a stepwise FGM material. If you remember, I've shown you a figure where I've shown you the stepwise FGM material and a continuous FGM material. So this is a manufacturing technique through which we can make a stepwise FGM material. Now, again, the disadvantage of this technique is that it can only be used to make stepwise structures. Now, for continuous structure, we usually go for centrifugal method. Now, in centrifugal method, what happens is that the difference in density of the material is used, and it is basically spinned. Basically, the powder is mixed, and then it is rotated at some speed. And because of the centrifugal force, the different different particles or different powders of different material settles at different position. Now, as you can already understand by the process, the major disadvantage of this material is that we cannot tailor performance. Basically, we cannot tailor the performance of the FGM material. Whatever material we are getting, we are getting. We cannot change basically the uh, gradual transition. Okay, the gradual transition is decided by depending upon the density of the particles which are used and depending upon the centrifugal force. So this is the disadvantage of this method, which there is a limit to which the gradient can be produced. Okay. Now the best method to produce functionally graded material is solid free form fabrication method. And the advantages, but this method can only be used to produce FGM at large volumes. Okay. So then only it will be less energy intensive and it can produce your structures at a very high rate. And also the material utilization in this process is maximum. Okay, no amount of material is wasted. As you can see that there might be some wastage in the physical vapor deposition technique, but in this technique there isn't any wastage. And with the help of this technique, we can make any type of structure with any complexity in the shape or design, or we can even basically uh, decide basically the gradual transition of the composition from top to bottom or from bottom to top. So these were the few of the techniques which are being used in the industries to manufacture the FGM. Now let's move on to the analysis approach. This is basically what my lecture is on and what we are more interested in. So starting with the basically what I'll be doing, I'll be discussing few of the uh, equivalent single layer theories which is used in uh, this analysis process, and then I'll be presenting you third order theory given by Dr. Reddy. I believe most of the people working in this area might already be knowing about Dr. J.N. Reddy. He's a great person with great intellect. And the second type of theory, which is again a higher order theory, I'll present that theory, which was given by Dr. Kim and Cha. So and then I have extended these theories to get the buckling results of the basically the critical buckling load for the FG plates. So let's start with the equivalent. What is an equivalent single layer theory? So equivalent single layer theory for a laminated plate are a heterogeneous laminated plate is treated as statically equivalent single layer. Okay, so we treat the layer as single layer despite of the different materials used. And obviously because we are treating it as a single layer, but although it is not a the composition is changing from bottom to top, so the constitutive behavior will change or it will be more complex. So if we talk about an aluminum bar or aluminum beam, so the deflection of that beam will be simply PL upon AE, but for this case, for the FGM beam, it will not be PL upon AE because the constitutive behaviors will be more complex, and which we will be seeing in the coming slides. Now I'll be comparing these three theories: the classical laminated plate theory, which is one of the most popular theory for plate analysis, and it was one of the most earlier theories given. And the second one is the first order shear deformation theory. The third one is third order shear deformation theory. So there are some assumptions associated with all these theories. Basically, as we are moving from classical to first order theory and from first order theory to third order theory, the assumptions are basically relaxed. Okay, so over here we are having three assumptions. Over here we are having only two assumptions, and over here we are having only one assumption. So obviously, since the assumptions in case of third order is less compared to the classical laminated plate theory, and it is a third order theory, so the results obtained from third order theory will be more accurate than first order theory, and the results obtained from first order theory will be more accurate than the classical laminated plate theory. And then I'll be telling you some disadvantage and advantage again associated with this theories. So starting with the classical laminated plate theory. So the assumptions are the transverse normal remains straight before and after the deformation. That means there isn't any bending of the transverse normal. Unloaded beam, the transverse normal of the unloaded structure will remain straight, and again after the loading or after the deformation, the transverse normal will again remain straight. So this is the first assumption. The second assumption says that the transverse normal do not experience any elongation. So if you are applying the basically the load in Z direction, so there won't be any elongation of the transverse normal, which means that the strain in that direction, okay, the strain in that direction will be equal to 0 because there isn't any elongation in that particular direction. And the third assumption in this classical laminated plate theory is that the transverse normal rotate such that they remain perpendicular to the mid surface after rotation. So again, the rotation of the normal is such that before deformation, it is perpendicular to the mid plane. Again, after deformation, it remains perpendicular to the mid plane. Now, the drawbacks of this theory, obviously, this is the computational effect is, in the classical lamination plate theory is less when compared to the third order theory. But there, because of which there are some drawbacks associated with this classical laminated plate theory. The first one is it under predicts deflection, and the second one is it over predicts natural frequencies and buckling load. And the reason for that it is because it is over basically it is giving you a stiffer structure, over stiff structure. The stiffness, basically it is increasing the stiffness of the structure than actual stiffness of the structure, and because of it, which it is under predicting deflection and over predicting the natural frequencies. And this is over basically over exaggeration of the stiffness is because of these assumptions where we are assuming that the transverse normal remains straight before and after bending, because of which the shear strains at the top and the bottom surface will be 0. Later on in this lecture, I'll be discussing the kinematics of deformation of this particular theory, where you will better understand how we have incorporated the basically the assumption in order to get the displacement field. Now, moving on to the second type of theory, which is the first order shear deformation theory. Now, in this theory, we have basically we have to compute 5 unknowns, and the assumption which remains valid for this theory is that the transverse normal remains straight before and after bending, or before and after deformation, and transverse normal do not experience any elongation, which means again that the strain in this direction of the transverse normal will again be 0. But the assumption which is relaxed in this case is that your transverse normal remain perpendicular to the mid surface before and after bending. This is not the case in case of in case of first order shear deformation theory. Now, the drawbacks associated with this theory is that it requires an arbitrary shear correction factor, which is always a pain to calculate because you need to calculate an extra factor, which basically depends upon the layup, the loading condition, and the boundary condition. And for that, we have the third order shear deformation theory, where we do not need to have any shear correction factor. It is more accurate than previously mentioned two theories. But obviously, the computational efforts in this theory is higher. And the only assumption which holds true for this case is that the transverse normal do not experience any elongation. That means the strain in the direction of the transverse normal is again 0. But the shear stresses at the top and the bottom surfaces will not be 0 in this case. So with this figure, you will better understand the difference between three theories. Now, this is an undeformed beam where the transverse normal is perpendicular to the mid surface. This is mid surface. This is our transverse normal. and this is our mid surface. Okay, so the transverse normal is perpendicular to the mid surface. This deformation is based on the CLPT, which is the classical laminated plate theory, where the transverse normal is even perpendicular after the deformation as it was before deformation. The transverse normal does not experience any elongation, and the transverse normal is straight before and after bending. Okay, it is straight, as you can see, it is straight before and after bending. For first order shear deformation theory, it is straight before and after bending. Okay, it does not experience any elongation. That means the length of this transverse normal will be equal to the length of this transverse normal. But this time, this angle is not 90 degree. Okay, the angle between the transverse normal and the mid plane is not 90 degrees anymore. So yeah, so basically what is happening in this classical laminated plate theory is that your transverse normal is basically rotating from this point to this, from this point to this point about this point O, if I call this point as O. Now the third figure shows you a deformed beam according to the third order shear deformation theory, where you can see that the transverse normal is no more straight before and after bending. Sorry, after bending. It was straight before bending, but it is not straight after bending. And the angle between the transverse normal is not 90 degree anymore. But the transverse normal hasn't experienced any elongation. So basically in this direction, if I call this direction as Z, so epsilon ZZ will be equal to 0 for all the three cases. For all these three theories, the epsilon ZZ will be equal to 0 because your transverse normal is not experiencing any elongation. Okay. Now, the displacement field of the third order theory is given by these equation, where you can see that this displacement in the z direction is only a function of x and y coordinate, and it is not a function of z, because it is not it is restricted. The elongation of this in this direction is restricted. And here again, I would like to tell you that the number of unknowns in this theory is again 5, and it was 5 in the first order shear deformation theory as well. But the third order shear deformation theory gives a parabolic distribution of the shear strain and the shear stresses, whereas this variation of shear stress and shear strain is linear in case of first order shear deformation theory. Now, these are the constitutive relations for isometric functionally graded material, where you can see that we are only using two material constant, which is E, or the equivalent E for this FGM in case of FGM, and the Poisson's ratio. Okay, only two material constants are needed for this type of material. And in the basically in the next slide, I'll be explaining you why only two material constant are needed and what is an isotropic FGM. So there are three types of material. The first one is isotropic material, the second one is orthotropic material, and the third one is anisotropic material. So an isotropic material is a material in which the properties are at any point the properties are same in all the directions. Okay, in any direction the properties are same, whereas in orthotropic material, the property at any point the properties are different at three mutually perpendicular direction, or the principal directions. And in anisotropic material is a material where at any point the properties are different at all the directions. Okay, so this is the basic difference between anisotropic, isotropic, and orthotropic. So since the properties are same at all the direction in isotropic material, that's why we need a lesser material constant in case of isotropic material. Now, this figure is basically showing you the mechanical behavior of various material. Here you can see that there is a cube of equal size or equal volume. This is a cube, this is a cube, and this is a cube of equal volume. And what we are doing is basically we are subjecting this cube to a normal stress. Okay, we are subjecting all these three cubes of different materials to the normal stress in this first row. and then we are studying the mechanical behavior of these materials. And in the second row, what we are doing, we are subjecting these material to the pure shear stress, and then we are going to basically study the mechanical behavior of this types of material. So starting with the isotropic material, the first figure over here shows you a cube which is loaded with normal stress. So what happens is that when a cube is loaded, isotropic material cube is loaded with a normal stress, there is an elongation in that particular direction in which you are applying the normal stress. And obviously there will be some reduction in the other two perpendicular principal material direction. Now, the important thing to note here is that there will only be, if you are applying only normal stresses, then there will be only elongation and contraction in the respective directions, and there won't be any shearing of the material. Okay. And the next thing to note is that suppose, obviously, we are having three principal material direction, and this load is applied, suppose in the first material direction. Okay, we are applying some stress sigma, normal stress sigma in the first material direction, and there we are getting some elongation as delta. We will call this as delta 1. Similarly, if we are applying the load in the second principal material direction of same magnitude sigma, then again we will get the same elongation in this direction, which we will call as delta 2. So for this particular isotropic material, delta 1 will be equal to delta 2 will be equal to delta 3. I hope this point is clear. Then that irrespective of the direction, in whichever direction you are going to apply the normal stress, the elongation will be same as long as the volume of the cube and the material of the cube is same, and the magnitude of the normal stress is same. Now coming to this figure, where we are applying a shear stress to same cube of isotropic material. Now in this case, what will happen? Only shearing of the material will take place, and there won't be any elongation or contraction in the principal material direction. There will only be shearing. So in case of isotropic material, what is happening in case when we are applying normal stresses, there is only elongation and contraction of the respective in the respective directions. And when we are applying shear stresses, there is only basically shear deformation, and isn't any elongation or contraction. So in order to quantify the deformation for isotropic material, we need only two material constant, which is Young's modulus and Poisson's ratio. So we could have also used shear modulus in place of Poisson's ratio. That would have also solved our purpose. But then I was more comfortable, and most of the researchers who have derived these theories are more comfortable with the Poisson's ratio. That's why they have taken Young's modulus and Poisson's ratio as the two material constant which are needed to quantify the deformation of an isotropic material. Now coming to the orthotropic material, again, when we are applying the load on a cube of orthotropic material, there will only be elongation in this direction and the contraction in the subsequent or the respective direction. But there is a difference in this case. I hope the concept of delta 1 and delta 2 is clear, from where we are getting delta 1 and delta 2. So what will happen in this case of orthotropic material, delta 1 will not be equal to delta 2, will not be equal to delta 3. It might be equal. It might happen that any of the two deltas are equal, but it is not necessary that these delta should be equal or these elongation should be equal. So what I'm saying is that if you are applying a normal stress on an orthotropic cube in the principal material direction 1, and the magnitude of the normal stress is sigma, then the magnitude of the elongation which you are getting in this direction will not be equal to the magnitude of the elongation which you will get when the same magnitude of normal stresses are applied in some other direction. Okay. And when you are going to apply the shear stresses, okay, when you are going to apply the shear stresses on this orthotropic cube, then also you will only get shearing deformation and there won't be any contraction or elongation. But this is only true when the loads are applied basically in the direction, in the principal material direction. Now, suppose I have a material, or if I suppose I have a material where the fiber angles are oriented at 0 degree and 90 degree. Okay, so if I am applying the load at 0 degree, there will be only what you call as elongation, and there will be contraction in the respective direction. But if I apply the load at an angle of 45 degrees, suppose this is your material, this is your orthotropic material, where you have fibers like this. Okay. Now, if you are applying the load over here in this direction, then you will only get the elongation in this direction and the contraction in the respective direction. But if you are applying the load in this direction, okay, if you are applying the load in this direction, then although you are applying a normal stress, you will get the elongation and contraction, and then as in the previous case. And with this, you will also get some shear deformation. Okay, you will also get some shear deformation. So if the loads are applied in the principal material direction, then you won't be getting any basically shear extension coupling. So in that case, if you are applying the normal load, then you will only get the elongation and contraction. And if you are applying the shear load or the shear stress, you will only get a shear deformation. But in case of where the load is applied at some angle, then in that case, there is a shear extension coupling. And in that case, despite of only normal stresses, there will be some shearing deformation. Now coming to the third type of material, which is an anisotropic material. Here you can see a cube of anisotropic material, wherein the normal loads are applied or the normal stresses are applied. But irrespective of the direction of the load, in any direction you are going to apply, be it in principal material direction or be it in any direction, you will get elongation in this direction and obviously the contraction in the respective direction, as well as some shearing of the material. And similarly, when you are going to apply the shear stresses on a cube of FGM, there will be shearing of the material as well as some elongation and contraction in the respective direction. So, and this is because there is a shear extension coupling in case of anisotropic material, and in case of orthotropic material, where the loads are applied at some angle. So I hope the difference in these three materials are clear to you. And in order to quantify the basically the deformation of the orthotropic material, you need at least 5 material constant, and that will depend again in the if this is the least amount of material constant that you need, and depending upon the situation, you might need more material constant. So moving further, this was basically the constitutive relation for isotropic FGM, where the stresses are related to strain. And we only, for FGM, since FGM is an isotropic material, so we only need 2 material constant. The first one is Young's modulus and the other one is Poisson's ratio. Now here you can see that I have shown only, I believe, 5 components of the stresses. That is because we are basically considering the 2D case where the stresses are in X and Y direction. And yes, and later on you will see that we can also take sigma XY or tau XY, tau XY or sigma XY equal to sigma YX. This is because the couple formed by these forces are equal and opposite. Okay, the couple force formed by these forces are equal and opposite. So this couple is equal to this couple and they are opposite. So we can take the magnitude of these 2 types of stresses equal. Or we can say that sigma XY is equal to sigma YX. Now this is how I have calculated the strain energy of the plate. Sorry, the Dr. Reddy has calculated the strain energy of the plate. Basically, he has used the principle of minimum potential energy, which states that material, when a material is deforming, it will basically deform to a shape which minimizes the potential energy of the system. So here he has used a variational, basically variational calculus approach, where the variation of the potential energy is made equal to 0, because according to the minimum potential energy principle, the material will deform to a shape where the potential energy of the system is minimized. Now these are the basically the stress, basically the moments and the stress resultant and the forces which are shown over here. And the stress resultant are related to the strain with the help of these equations. And the A, B, D, E, and H matrix are calculated with the help of these equations. These equations I have used to make the in-house MATLAB code. That's why I am showing you. And the boundary conditions are satisfied with the help of Navier's solution, where these constants are made equal to 0. So these are the boundary condition. Here I would like you to emphasize on this condition, and maybe this one and this one. So I'll be explaining you that when we are going to take the Fourier expansion in order to satisfy the boundaries with simply supported boundary conditions. So how we have assumed the solution, I'll be telling you. So this is the basically Fourier expansion which I have assumed, or sorry, which has been used in order to basically satisfy the boundary condition. So if you consider this first expansion, where alpha is equals to m pi by a, and this beta is equals to n pi by b. Okay, so since we are talking about plate, that's why a and b. Now this u naught, I have already underlined this. This u naught has to be 0 at y equal to 0 and at y equal to b. So coming back to this equation, if you put y equal to 0, obviously this will give you sine 0, which will be equal to 0. So u naught will be equal to 0 at y equal to 0. And if you put y equal to b, then again you will get sine n pi, because this complete term will become n pi upon b into b, and this will y equal to b. So this will cancel out and you will get sine n pi, which is again equal to 0. So your u naught is equal to at y equal to 0 and y equal to b. So this was needed. This was basically the boundary condition which we need to implement with the assumed Fourier expansion. And this is very much true, because as I have already showed you that it is equal to 0, u naught is equal to 0 at y equal to 0 and y equal to b. Similarly, I can also prove for v naught at x equal to 0 and x equal to a, and for phi x and for all the other components. But I will only again show you for w naught, where it is 0 at y equal to 0 and y equal to, here it should be b, at y equal to b, and again at x equal to 0 and x equal to a. Okay, so again, since w naught is to be 0 at all the four boundaries, that's why we have basically the assumption is that basically the expansion is in terms of sine. So again, it will be 0 obviously when we take x equal to 0 and y equal to 0, and it will be again equal to m pi, sine m pi, and sine n pi in case of x equal to a and y equal to b. So it will come equal to 0 at x equal to 0 and x equal to a, and y equal to 0 and y equal to b. I hope this expansion and this assumption is clear to you. And this is the one of the reason why the analytical solution is only possible for simply supported plates and not for other types of boundary condition, because these we don't have any proper assumptions to make in order to satisfy the boundary conditions. So as I told you, your alpha is equals to m pi by a and beta is equals to n pi by b. And this is the load which I have used in my analysis, which is a sinusoidally varying load. These are basically giving you the stiffness matrix coefficients. This is how I have calculated, or basically this is how I have computed using my MATLAB code. So these are all the components of the stiffness matrix. And over here is the mass inertia matrix. And these are the components which has been used in this in order to calculate the stiffness and the mass inertia matrix. Now the fundamental needs natural frequency is obtained with the help of these equation. I have obtained the eigenvalue. This is an eigenvalue problem where I have obtained the eigenvalues of this equation in order to get the different modes of basically the natural frequencies at different modes. I'll show you what I have obtained in the coming slides. So again, as I told you this that this buckling calculation has or the buckling derivation has been done by myself only. And buckling, before that, let's understand what is buckling. So buckling is basically out of plane deformation. Suppose if I have a plate in XY direction and the loads are applied either in X or in Y or in both the direction. So out of plane direction is equal to is basically what is buckling. But then the cylinderness ratio should be greater than 80. Otherwise, in case of buckling, crushing will happen. Generally, this crushing phenomena is in case of columns and not in case of plates. But just because it is there, that's why I'm explaining you that in case of columns, the cylinderness ratio should be greater than 80 in order to basically call the deformation as buckling. And it is a large lateral deformation, which we are calling as buckling. Now, over here, you can see that this is the NXX is the load which is applied in X direction, at which the buckling start, or we can also call this as a critical buckling load. And NYY is the load which is applied in the Y direction. Again, at this load, the buckling will start, and we are calling this load as critical buckling load in Y direction, and then NXX as critical buckling load in X direction. So if you are applying the load only in the X direction, that type of buckling is known as uniaxial buckling. Obviously, in this case, to buckle, you will need a greater load. And if you are applying the loads both in X and Y directions, then that type of buckling is known as biaxial buckling. And obviously, since you are applying the load from both the directions, the magnitude of the critical buckling load will be less in this case. Okay, and since the plate is in XY direction, the deformation will be in Z direction because for buckling it has to be out of plane deformation. Now this is how I have calculated this buckling load with the help of this equation. Again, this is an eigenvalue problem where I have calculated the eigenvalues in order to get the critical buckling load. And this value of kg is taken from this reference number 36. And this is the value of kg where alpha and beta are same, which is your n pi by a and m pi by a and n pi by b. Now coming to the next theory, which is higher order theory, which is again given by Dr. Kim and Chow. Now, first of all, I'd like to basically tell you the difference between third order theory and higher order theory given by Kim and Chow. So in this theory, we have only 4 unknowns. So the computational effort is again reduced when compared to the third order theory. And it is giving you the parabolic distribution of shear stresses and shear strains. So it is as good as third order theory. Now, since we have talked a lot about higher order theories, and this is again a third order theory, which we are calling as higher order theory. So this is a good time to tell you why don't we use a fourth order or a fifth order or a nth order theory. That is because obviously if we keep on increasing the number of the order of the theory, the results will increase. But after the third order, as in case of third order theory, when we move from first order theory to third order theory, the results have improved significantly. But if we move further from third order theory to fifth order theory to seventh order theory or to nth order theory, what will happen? The computational effort will increase. It will increase to a large extent. Okay. And the improvement in the result is not that significant. The marginal improvement in the results. So that's why we don't use this third order. Any theory is greater than third order theory. And anyhow, the analytical results are becoming more obsolete day by day because we have a great tool which is known as finite element method and finite element analysis. There are great softwares which are used to analyze the system. And this FE modeling is also a very good tool. I have been using this FE modeling since a long time, and it is very good. And there is also an extended FEM, which we call as extended finite element method, used for by the fracture mechanics people, wherein you can predict the crack propagation. Basically, extended FEM is used to find out the solution or of the differential equations with discontinuous functions. This is important because finite element method, what it does, it simplifies the differential equation into an algebraic equation with continuous functions. But extended FEM, what it does, it simplifies a differential equation, a partial. It may be partial, or it may be basically it is partial differential equation. And XFEM, basically what it does, it simplifies this partial differential equation into an algebraic form for discontinuous functions as well. Anyhow, this is out of the scope of this lecture discussing about XFEM, but just it came to my mind that that's why I've discussed this with you. Now, yeah, the assumptions associated with the higher order theories is that it assumes that the in-plane direction, that means the in-plane displacements, that means the displacement in X and Y direction, and the transverse displacement, that means the displacement in Z direction, are partitioned into bending and shear components. Okay, both of these types of displacements are partitioned into bending and shear components. And the second assumption is that the bending part of the in-plane displacements are similar to those given by classical plate theory. And the third assumption is that the shear part of the in-plane displacement of the plate are taken in such a way that shear stresses vanishes at the top and the bottom surfaces of the plate. So that means we don't have any shear stress at the top of the surface and at the bottom of the surface. That's how Dr. Kim and Chow has assumed the shear part of the in-plane and transverse displacement. Now, this is a good point to explain the kinematics of deformation of the classical plate theory, because the bending part of this higher order theory is similar to those given by the classical plate theory. So let's see the kinematics of deformation based on the classical plate theory. So in the first figure over here, you can see a beam which is undeformed, and AB is the transverse normal. This is your X direction and this is your Y direction, and perpendicular to the screen is your Z direction. Now we have to basically study the kinematics of deformation, so we have to apply the loads in X, Y, and Z directions. So if we apply the load in Z direction, that will be the load in the transverse direction, and if we apply the load in X and Y, so what will happen if we apply the load in X and Y direction? There will be stretching of the beam, or it's better to say that there will be a stretching of the transverse normal. This is your transverse normal. So depending upon the magnitude of the direction of depending upon the direction of the load in this, whether it is in positive X or whether it is in negative X, this transverse normal will be stretched towards right or towards left. So since we are applying the load in the positive X direction, that's why you can see this is the deformed case where the transverse normal has stretched from this point to this point, and now we are calling this new transverse normal as A dash B dash. This is same, only thing is that because of the application of load in the positive X direction, it has stretched towards right. Okay, and the magnitude of this direction is U naught X, which is dependent upon X and Y only. It is not dependent upon Z coordinate. So any normal to the midplane is basically translated horizontally towards right or towards left, depending upon the direction of the load, as a rigid line. Okay, this is important. There is no deformation of the transverse normal, only it is getting stretched towards right, since the load is applied in the positive X direction. And similarly, if you apply the load in Y direction, in the positive Y direction, if you talk about a plate, and if you apply the load in the positive Y direction, your transverse normal will get stretched in the positive y direction, and that the magnitude of that will be v naught, which will be dependent again on xy. Okay, so since the case of u naught and v naught are same, and the case when we are applying the load in the x direction and y direction is same, so I have only shown you in one direction, where there, because in both the direction there will be stretching of the transverse normal, only the magnitude on x and y direction will be different. Okay. Now, this is the second type of deformation. That deformation was because of the stretching, and this deformation is because of the bending. Again, this is your undeformed beam, and this time we are showing this beam in xz plane. This is your x direction and this is your z direction, and AB is your transverse normal. Okay, AB is your transverse normal, and this is an undeformed plate. Now, any normal to the midplane is translated vertically as a rigid line maintaining xy coordinate. Okay, it will move down as a rigid line. So if suppose if I am applying some load in the positive z direction, so what will happen? There will be two types of there. Basically, this deformation will be in two steps. The first one will be this transverse normal will move down by a magnitude w naught, which is again dependent upon x and y coordinate, and there will be a rotation of the magnitude, sorry, of the transverse normal. But as you can see that in classical plate theory, the transverse normal before and after bending remains perpendicular to the mid surface. Okay, and it does not experience any elongation, and it does not that's why this is not dependent upon z. That's why it is not dependent upon z and only x and y, because the transverse normal cannot experience any elongation as per the assumptions of the classical plate theory. But what is happening is that if I call this point o as, sorry, if I call this point as o again, okay, this point is o, so what is happening, your transverse normal is getting rotated about this point o. Okay, so in two steps the deformation is taking place. The first step, the transverse normal is basically translated vertically downwards because the load is applied in the positive z direction as a rigid line maintaining x and y coordinates. X and y coordinates are same, only the z coordinate is changing, and then what is happening, the transverse normal is getting rotated. So we can basically divide the deformation due to bending into two components, and there are deformation basically because of the bending as well as because of the stretching, and we have studied both the deformations separately. Now what we are going to do, we are going to superimpose both the type of deformation, because actually there will be both the things will be happening simultaneously. So what are the things which are happening simultaneously? Your transverse normal is getting stretched in positive x direction by a magnitude u naught, and your transverse normal is getting translated downwards by a magnitude of w naught in the positive z direction, and it is also getting rotated about this point o. Okay, and this angle of rotation we will call this, sorry, in the next figure it will be more clear, we will call the angle of rotation as alpha. So this is how actually the kinematics of deformation is working in case of classical plate theory, where the transverse normal is getting stretched as well as it is getting deformed because of the bending. Now this is a figure which will help you to understand the mathematics behind the deformation, and it will help you to quantify the deformation, and in order to derive the deformation fields in x, y, and z direction. So this is your x direction again, and this is your mid plane. Okay, this is your mid plane, and this is your positive z direction. So basically the mid plane is shown in the x z plane, and this angle is alpha. Okay, this angle is alpha, and similarly these two angles will also be alpha. These two angles will also be alpha. Now if you take the tangent of this angle alpha, it will be equal to delta w upon delta x. And since we are talking about small deformations, so your tan alpha will be equal to alpha. Okay, your tan alpha will be equal to alpha. So your alpha is equal to del W upon del X. Here I have changed from delta to del because we are talking about a small deformation. This equation was written for large deformations and this equation is written for small deformation. So alpha will be equal to del W upon del X. Now, the idea behind this exercise is to quantify the deformation of a generic point on the normal. Any generic point, it could be any point. So your transverse normal before bending is AB, as shown here. It is, sorry, A, B, and the deformed or the rotated transverse normal is A dash, B dash. Now, mind it that the length of AB will be equal to A dash B dash because of the assumption that the transverse normal isn't experiencing any elongation. Now, suppose I have taken a point P on the undeformed transverse normal, any point P which is at a distance Z from the midplane. After rotation, this point will become P dash. Now, if I call this point as O, so what is happening is that basically it is rotating about O from P to P dash. And since there isn't any elongation in the transverse normal, therefore the length of OP will be equal to the length of OP dash. Okay, and this length can be taken as equal to Z del W upon del X. Okay, that's how I have basically shown you the in-plane deformation due to rigid rotation. Rigid because there isn't any elongation, there isn't any basically deformation of the transverse normal. Only thing it is rotating. That's why we are calling it as rigid rotation to the normal. Here you can see that I have already placed, I have also placed a minus sign before this magnitude which I have derived over here. That is because we have taken the downward direction as positive Z direction. So this direction will be obviously negative Z direction and this magnitude will be negative Z. That's why I have placed a negative sign over here. So the in-plane deformation due to rigid rotation of the normal will be equal to minus Z del W upon del X. Now, obviously, there was two types of deformation, which is your stretching as well as this deformation will also be added in case of X. Okay, so if we are talking about the region above the midplane, this amount will be added to U naught if we are talking about the displacement in X direction. And if we are talking about the region below the midplane, then this amount will be subtracted from the U naught. Okay, so the displacement field in case of classical plate theory, which you have already seen, is given by U, which is equal to U naught minus Z del W upon del X. That's what we have derived over here. Okay, the deformation in the X direction will be equal to U naught minus or basically plus minus of Z del W upon del X, and this minus is coming from this because of the this height is in the negative Z direction. In a similar fashion, we can also prove or we can also come to the conclusion that the deformation in the Y direction will be equal to V naught minus Z del W upon del Y, where V naught is because of the stretching and Z upon del W upon del Y is because of the bending. And lastly, the W, the deformation in the Z direction, which we are calling as W, will be equal to W naught. Again, this is a function of X and Y coordinate and not Z because there isn't any elongation in the Z direction. The transverse normal need to be of same height as in before and after bending. Now, it is interesting to see that these are the components which are contributed in the displacement field because of the stretching, the deformation because of the stretching, and these are the deformation coming out from the bending part. Again, with this, by looking at the displacement field, I can tell you, or you can also see that how I have satisfied or how it has been, the assumptions has been satisfied. So the first assumption was that there isn't any elongation of the transverse normal. So that means your epsilon z equal to 0. And that is the case if you try to take the derivative of W with respect to Z, that will be equal to 0. Similarly, if we talk about u or v direction, so the other type of assumption was that your your transverse normal will remain perpendicular to the midplane and it will remain straight before and after bending. So if there is any shearing at the top and bottom surface, it will look like this. Okay, if there is shearing at the top surface and bottom surface, it will look like this, and this angle won't be 90 degrees. So that means that the shear stresses at the top and the bottom surfaces is equal to 0. And if you try to find out the shear stresses in the basically uh, the shear stresses at the top and the bottom surface, you will get it equal to 0 with the help of these two displacement field. So just by looking at the displacement field, I can also explain you how basically the assumptions have been met in order for the derivation of this displacement field. So I hope the kinematics of deformation of the classical plate theory is clear to you, because that is important in order to understand the higher order theory. Now, coming back to the higher order theory, the assumptions which we made is that the in-plane and the transverse displacement are partitioned into the bending and shear components, and the bending part is same as the in-plane displacement of the classical plate theory. So that means that we have already achieved this part. Okay, we have already achieved this part. Now coming to the second part, the shear part is basically taken such that the shear stresses become 0 at the top and bottom surfaces. So these are the displacement field for the higher order theories which you will get, wherein you can see that this these parts of the underlying parts of the displacement is same as the classical plate theory. Only addition are these parts, okay, which the author is calling as shear components, and the shear components are chosen in a way where the basically the shear stresses are becoming 0 at the top and bottom surfaces. Now again, it is important to note here that the shear component in case of the deformation in the third direction is not dependent upon z, because had it been dependent upon z, then that means that there is some elongation of the transverse normal in the z direction, which is not the case. So again, in this case also, epsilon zz will be equal to 0. Now these are obviously the strains, how we have calculated the strains. So what we haven't done anything. Basically, we have differentiated these displacement field with the respective differentials to get the epsilon x, y, and the other components. Again, you can see that epsilon zz is not shown here because epsilon zz will be equal to, or epsilon z will be equal to 0, as it isn't experience any elongation. The transverse normal is not experiencing any elongation. Now this equation will show you the relationship between the stress or the constitutive relationship, the stress and strain relationship. Again, you can see that since we are talking about the functionally graded material and it is an isotropic material, that's why we only need two components or the two material properties, which are Young's modulus and Poisson's ratio. And in the previous slides, I have already explained you why you need only two material constant for an isotropic material. Similarly, the author has also followed the footsteps of Dr. Reddy, and he has also written the strain energy, because the idea is same, to minimize the potential. Basically, the variation of the minimum potential energy is equal to 0. These are your stress resultant. These are your moments, and these are your moments because of the shear force, and these are your forces. Okay. And this is how you are going to calculate the mass inertia matrix. This is the relationship of the stress resultant with the strain, wherein this component is basically showing you the strains because of bending, and this component is showing you the strains because of shear. This is how we have calculated an A, B, D, E, F, and H matrix. And these are the same expansion. These expansions are again, the Fourier expansions are based on the Navier's approach. In order to basically apply the Navier's approach of the simply supported boundary conditions, these expansions have been used. And if you can see, these are very much similar to the previous expansion. Over here, you will get u equal to 0 at at y equal to 0 and y equal to b. Similarly, you will get v equal to 0 at x equal to 0 and y equal to b, at x equal to a. Sorry for the confusion. This is x equal to a. And WB and WS will be basically the deformation because of bending and shear, which will be equal to, both of them will be equal to 0 at x equal to 0 and x equal to a, and at y equal to 0 and y equal to v. So this is basically the same type of assumption which we have already used in the third order theory. And where alpha and beta have same meaning, alpha is equal to m pi by a and beta is equal to n pi by b. And a sinusoidally varying load has been considered in x as well as in y direction. And again, the same equation is used to calculate the natural frequency. I have taken the values. Basically, I have calculated the eigenvalues of this problem, wherein the different eigenvalues are giving you the different modes of vibrations. And this is the stiffness matrix, and you can see that the stiffness matrix is way smaller compared to the third order theory. And these are your mass inertia matrix. Now, coming to the material modeling approach, I would request you to take a break of just a minute at this point. I'll take a break of only 1 minute at this point, and I'll be back in a minute. Okay, so thank you for your patience, dear participants. Now, we will start with the material modeling of functionally graded materials. And this basically, the idea in the material modeling is to first of all find out the volume fraction of the material A and material B. As by now you have understood that we are using two material in order to form a FGM whose composition is changing along one dimension. Generally, basically the composition is gradually changing in the height direction, so, or in the thickness direction. So the idea is to first of all calculate the volume fraction of the first material and the second material. So as I told you that generally we use ceramic and metal to form the functionally graded material, and I have also used ceramic and metal in the function in order to perform the analysis of functionally graded materials. So we will call VC as the volume fraction of the ceramic, and we will call VM as the volume fraction of metal, which is varying along Z direction. Okay, this variation is dependent upon some function, which I'll later on tell you. So this volume fraction of ceramic is calculated by this formula, which is Z by H plus 0.5 raised to the power N. where n is a non-negative parameter, which we call as inhomogeneity parameter. Okay, inhomogeneity parameter. And the volume fraction obviously of metal, because we have only two components, will be equal to 1 minus Vc, which is 1 minus the volume fraction of the ceramic part. And for this particular study, the Poisson's ratio is assumed to be constant. And had it been any different, we could have used the same method as we have used to calculate the Young's modulus and the density. We could have used the same formula to calculate the Poisson's ratio as well. But the materials which I have chosen for the analysis purpose happens to have same Poisson's ratio. Now, the Young's modulus can be calculated with the help of these three, basically these three equations or formulae. This is your modified rule of mixture, this is your rule of mixture, and this is your Mori-Tanaka method. Now, as you can see that at Mori-Tanaka method, I have given a thumbs up. At rule of mixture, I have given a thumbs up, but I have given a thumbs down to the modified rule of mixture. That is because the modified rule of in case of modified rule of mixture, this is the equation which is used to calculate E at any point Z. Okay, E is your Young's modulus, obviously, where a factor of Q is needed, where you need to perform experiments in order to get the stresses in the ceramic part, stresses in the metallic part, strain in the ceramic part, and strain in the metallic part. Since I have performed analytical study, that's why I couldn't perform the experiments, and that's why I couldn't use this modified rule of mixture, which is the reason for me to give a thumbs down to the modified rule of mixture, nothing else. This is again a good method. It gives great results, but for me it is not useful because I could not perform the experiments. Coming to the second type of method, which is rule of mixture. With the help of rule of mixture, this is how you are going to calculate the Young's modulus and the density, wherein the Young's modulus is equal to the Young's modulus of metal, Young's modulus of ceramic minus metal. Okay, ECM is ceramic minus metal, and this is the volume fraction of the ceramic. Now, actually, the rule of mixture says that the Young's modulus at any point Z will be equal to the volume fraction of metal and the Young's modulus of metal plus the Young's modulus of ceramic into the volume fraction of ceramic. This is your actual rule of mixture. Now if you put the value of volume fraction of metal over here, which is 1 minus Vc. So if you put this value, you will get this equation. So this will be transformed as Em, which is the Young's modulus of metal, minus Em into Vc plus Ec into Vc. So if you take Vc as common, you will get Ec minus Em. Okay, so this is the same equation which is written over here, where Vc, or the volume fraction of ceramic, is equal to this, which is equal to 0.5 plus Z by H raised to the power N1. Okay, now this is the same equation. I've just put in the value of volume fraction of metal in terms of volume fraction of ceramic. Similarly, you will get this equation for the density, which says that the density of metal, density at any point Z is equal to density of metal plus density of ceramic minus metal plus the volume fraction of this ceramic. Now over here you can see that I have written N1 for Young's modulus and N2 for density, for calculating the density. So N1 and N2 are basically the inhomogeneity parameter or the power law index, which might be different to calculate the Young's modulus, or it might be same. So for my study, it will be both the power law index N1 will be equal to N2 for all the cases until otherwise stated. Okay, so I'll let you know when I am taking this N1 and N2 differently. Otherwise, in general, it will always be equal. Now, this is the Mori-Tanaka method to calculate the Young's modulus. And similarly, if you replace Em with rho m, and if you replace Ec with rho c, you will get the density. Okay, you just have to replace this this thing with rho m, and this thing with rho c, and all the other components. Now, as I've told you, somebody has already asked this question in the beginning of the lecture. So I told you that I have, as for the metal part, I have only used aluminium. Okay, and for the ceramic part, I have used alumina and zirconia. So basically, I am having two system: alumina, and aluminium zirconia systems. Okay, and the performance of these two systems you will see in the coming slides. And in this particular slide, I have this system A and system B. In this particular slide, you can see the material properties of these types of system. These are the densities given in kg per meter cube, and Young's modulus is given in GPa. And as I've already told you, the Poisson's ratio happens to be constant in all the three materials. Had it been any different, for example, had it been something else, say 0.4. So what would we have done? We would have used our rule of mixture, which says that the Poisson's ratio at any point z will be equal to the Poisson's ratio of metal multiplied by the volume fraction of metal plus Poisson's ratio of ceramic, which is 0.4, multiplied by the volume fraction of ceramic. This is how we would have calculated if the Poisson's ratios would have been different. But for my analysis part, it happens to be same for all the three cases. So this is the load which I have considered, wherein the load is varying in x direction sinusoidally, and it is varying in y direction also sinusoidally. Now I have presented all the results in non-dimensionalized form, because that's how we present the results, just so that the comparison become easy and the units does not play any role in the comparison. So these are the equations which I have used to non-dimensionalize all these parameters. This is W, which is the central deflection. Sigma x is the stress in x direction, and so on. This is the natural frequency. For natural frequencies, I've used two equations, because the equation used in the literatures were different. So just to compare the results, I've used two different non-dimensionalized equations. Now, this graph over here basically shows you the variation of the volume fraction of the ceramic. Okay, this is the volume fraction of the ceramic with with basically normalized thickness. Okay, with normalized thickness. Now, if you see, if you take the inhomogeneity parameter n equal to 1, then this is the case where the variation of the volume fraction of ceramic is linear. From this is the volume fraction where it is 0. That means at this point the material is having 100% metal, and at this point the material is 100% ceramic. So the transition from metal to ceramic is linear. Okay, when we are taking n equal to 1. Now it is also interesting to see that when we are taking n equal to 0, the volume fraction is coming out to be 1, because anything raised to the power 0 is obviously 1, and the volume fraction of ceramic is your 0.5 plus z by h raised to the power n. So if n is taken to be 0, then the volume fraction throughout the thickness of the plate will be ceramic. In other words, the plate will be completely of ceramic. And similarly, if we take n equals to infinity, the volume fraction of this is the case where n is taken as infinity. This is a straight line where the volume fraction of ceramic will always be 0 throughout the thickness of the plate. In other words, the plate will be completely or 100% made up of metal. Now, you can see the other cases where n is greater than 1. The plate is basically metal rich. Whenever n is greater than 1, plate is metal rich, or the volume fraction of the metal part is greater than the volume fraction of the ceramic. On the other hand, if n is less than 1, plate is always ceramic rich. Okay, plate. So as we keep on increasing the n, the plate will becoming more and more metal rich. Okay, plate or whatever your structure is will become more and more metal rich. And if we take the values of n less than 1, then it will be ceramic rich.
It is sorry to disturb you,
Ji.
Pradeep.
No
Sir,
problem.
there is one question. You have shown that kinematics of deformation for classical plate theory and then showed the displacement field for the same.
Yeah,
So
yeah.
can you explain how the assumption just in this theory are satisfied?
Okay. I'll tell you. I got your question. Let me move on to that slide again. Yeah. So you are asking that just by seeing at the displacement fields, how can I say that the assumptions are met? If I am right, is this your question?
Yes, this is the same.
Okay. Thank you. So what were the assumptions? Let's recall the assumptions. So assumptions were that your transverse normal will not experience any elongation, and then your basically the transverse normal will remain straight before and after bending, and your transverse normal will be perpendicular to the mid surface before and after bending. So considering the first assumption, which says that your transverse normal does not experience any elongation, that means in that direction, if the strains are zero, we can say that the transverse normal is not experiencing any elongation. So if you consider this displacement field in z direction, which says that w is equal to w naught, which is a function of x and y only and not the function of z. So if you differentiate this w with respect to z to get your epsilon zz, you will get this thing equal to 0, because this is not a function of z, so you will get 0. So that's how we can say that the transverse normal is not experiencing any elongation in z direction. Other assumptions are that your transverse normal is basically perpendicular and it remains straight. So as I have already explained that if you are having shearing at the top and bottom surface, this angle will not be equal to 90. So if we are assuming that this angle is equal to 90, that means the shear stresses at top and bottom will be equal to 0. Okay, the shear stresses at top and bottom will be equal to 0. Now, if you calculate the shear
I
stresses,
would like to interrupt Mr. Ateeb. Can you
no
please
problem.
conclude now? Because from 12 noon, we are scheduled to have one test for the participants. So kindly, we'll request you to
Okay.
kindly conclude your talk.
Okay. Sir, can I get 5 more minutes, because I
Yeah,
have a
yeah,
lot to
please.
show, but
Yeah,
I'll
sure.
just hurry up. Okay.
Okay.
Okay. Okay. So just I was not even able to get to the results part, but nevertheless, the time was always an issue. So here you can see, I will share this presentation with the organizers, and hopefully you will get these presentation, and you can always go through the presentation. In case of any queries, you can always write me. I will also give my email ID, and I'll be happy to answer any queries from your parts. But for now, you can see that this is the variation of the Young's modulus with the normalized thickness, and it is again same as in case of the volume fraction. At n equal to 1, the variation is linear, and at n equal to 0, the plate is 100%. As you can see that the volume fraction is 1 throughout the thickness of the plate. So that's why the Young's modulus is coming out to be the Young's modulus of your ceramic, and at n equal to infinity, the Young's modulus is coming out to be the Young's modulus of metal. And if you are taking n greater than 1, then the plate is metal rich, and if you are taking n less than 1, then the plate is ceramic rich. And these two are for Young's modulus and density, and the observation is again same in both the cases. This is for other material where we have considered aluminum and zirconia. The observation is absolutely same in this case also. So these are the dimensionless central deflection for AL2 square, basically aluminum and alumina square plate under sinusoidal load at the central position. Now here it is important to note that as we keep on increasing the inhomogeneity parameter, or n, the deflection is increasing. And the reason for that, as I have already explained to you, for n greater than 1, the plate is turning out to be metal rich. The plate is turning out to be metal rich, and as you know that ceramic is more stiffer, and stiffness is basically the resistance to your deformation. So that's why as you keep on increasing N, the plate is becoming more metal rich and it is becoming less stiffer. That is the reason why you are getting more that is the reason why you are getting more deformation. Similarly, on the other hand, as you keep on increasing N from zero, as you keep on increasing N, the natural frequency will keep on decreasing because the plate is getting less stiffer for the same reason as I have explained you before. So these are some results where where I have also varied N1 and N2 separately. N1 was the inhomogeneity parameter for the variation for calculating the Young's modulus, and N2 was the inhomogeneity parameter for the density part. But since this is a very interesting observation, where you can see that as we increase S, the difference is not that much, and as the S is decreasing, the difference is large in case of N equal to 0.5 and N equal to 10. S is basically a ratio of A by H, where A is the length of the plate and H is the thickness of the plate, which for my analysis purpose is taken unity in all the cases. Basically, what is happening when the size of the plate is increasing, the deformation is same for most of the cases. It is not N sensitive, or it is not inhomogeneity parameter sensitive, but for a smaller plate it is more sensitive, and for N2 it is not that sensitive for either for small or the large plate. But the observation is same. Again, the variation over here is more compared to over here. So since the time is already over and you people are having a test, I believe at from 12. But again, I also want to tell you, this is again a very interesting observation where you can see that the mid plane for the FGM plate is not at the center. Till now we have studied for all the metallic plates or for the composite plate, mostly the mid plane is at the center. But for FGM plates, the mid plane is not at the center. I would have discussed the method to calculate the mid plane, but again, due to the shortage of time, I cannot do that. Uh, these are the buckling results which you can go through. And at last, I have some techniques to model these structures in Abacus. But I believe I have already made the presentation in a way where you can understand how the results are varying and how the things have to be done. But nevertheless, if you have any queries, you are most welcome. I love to answer your queries via email or via WhatsApp chat. Okay, so thank you for your time and thank you for listening my lectures patiently. And yeah, thank you to the organizers also, Dr. Imran and Dr. Asfar. Thanks a lot for inviting me for this talk.
Thank you, Dr. Ateeb, for
Yeah.
delivering a wonderful and informative lecture.
Yeah.
Now, if there is any question, then the participant can send an email to the resource person directly, because we have a shortage of time right now. We have a test scheduled at 12 noon. So thank you, Dr. Ateeb, for the talk.
Yeah, most welcome, Dr. Asfar. And yeah, thank you again for inviting me. And I'll be sharing the presentation with you. Kindly share the presentation with the concerned participants and my email ID and my WhatsApp number as well.
Sure, sure.
So I'll be leaving now. Thanks a lot.